All right, good morning everyone. So we're going to start the fifth technical session today. My name is Gauri Shankar Ramachandran, so I'm a postdoctoral researcher at the University of Southern California. So we have three exciting talks in this session. They are broadly coming under the topic of information sharing applications. Our first speaker in this session is Nelson Bohr, who is going to give a talk on promoting distributed trust in machine learning and computational simulation. Nelson Bohr is a research engineer at IBM Research Africa, and he's a member of the industry's research group focusing on healthcare, finance, agriculture, and education applications by combining blockchain and artificial intelligence. And his other research interests include distributed systems, Internet of Things, blockchain, and edge computing. And he also BSc in software engineering from University of Eastern Africa, and he also holds an MSc in computer science from Georgia Institute of Technology. Nelson, I'll give the floor to you. Take it away.
Thank you. Good morning. Thank you so much for the talk. I'm going to take you through promoted distributed trust in machine learning and computational simulation. This is a build-up on the work that I talked about yesterday, and we've done in collaboration with IBM Research in Kenya and Yorktown, and the University of Illinois and the University of Oxford. I'll build up on the introduction that I talked about yesterday concerning the policy decisions and the increasingly dependent on the simulations of machine learning models. And so it really cuts across different fields, and precisely in our specific domain of disease modeling community, it becomes a very necessary aspect to look into. And in this case, we have different disease modeling scientists who run simulations in a distributed fashion, where inputs and outputs really generated are consumed by remote parties. And in this case, it calls for the need of those simulations at a minimum to be tracked and audited, either through algorithmic accountability or decision provenance. So in this case, we're just keen on being sure that whatever we are running, and the premise here is it's healthcare, it's very sensitive, so we need to be able to audit and, track the information. Just give it a second. There you go. Looking at some of the things that also we've done is the aspect of being able to algorithmically say that it's fair for data and accountability and transparency. And so in this case of fairness, accountability, and transparency, the outcomes associated really in the disease modeling community is very important because of the suboptimal outcomes that have direct impact to human lives. So we cannot play around in that area. So, and also depending on the specific disease being modeled, also the location of that, and also the scenario of sharing that data, and the validation and the development also brings in the different aspects to make it even more complicated. And also to build on that as well, if you have limited computing resources, like for some of guys we worked with in Zambia, so they're out in the field, and so there's an aspect of limited resources and ability for them to securely access or even extend and trust models from others. So there's that aspect of the need of trust. And so blockchain really aligns perfectly to that domain because it improves the transparency, integrity, and security of transactions that are involved among participants. So the algorithms, the protocol we've talked about in this conference helps to replicate and ensure the consistency of each ledger copy. Then also the transactions providing the consensus is also important. And so really blockchain aligns perfectly. But one person would ask then, so what have you done in addition to current blockchain existing architecture? Just before I get into that question, I'll just want to pinpoint the specific challenges for the disease modeling communities scientists. One is the ability for them to share data in a trustable and reliable way from a distributed setting, and so hence the aspect of blockchain fitting in perfectly to that. Then we also have the detection and the elimination of invalid results from the previous transactions and the model outputs. And so this point number 2 is where we saw that we can build and extend the existing approach of blockchain based on my talk yesterday to enable us to give us a digital trust, and also the we have different players in the industry who have resources in terms of computing. Can we leverage on what we have or even what other people are having, and we aggregate them in a form that we can give it to the disease modeling community, either open source or monetized. So I'll focus on point number 2, since the rest are a bit kind of straightforward. So number 2, looking at the blockchain endorsement process, we know that it helps to validate the identities that sign the transaction, validation of the signatures and the endorsers on the transaction, and also it ensures the transaction satisfies a given endorsement policy. And so one question that we ask ourselves, looking at the disease modeling community, can we then bring in another aspect and say that we want to be able to learn and make decisions from the previous transactions? And in this case, we want to bring in another endorsement layer and say, endorsement process and say, before you endorse, in addition to what the blockchain currently does, we want to say that before we endorse a given transaction, before an agent endorses a given transaction, can they make that decision based on my previous space or previous domain or previous data that we have that has been learned over time? So that is where we are saying that we can extend now and apply to disease modeling community. And of course, the reasons behind this are what I've pointed out, because of the suboptimal, the need of being sure of what you're logging onto the ledger. And so our use case really is malaria. And why malaria? It's because it's global. And for us, we are building a consortium that will help us explore the need of addressing trust. And so we are using the epidemiological machine learning model called Open Malaria. So it's really open source, but it also gives us the ability to share freely with different users out there. So on the infrastructure, like I pointed out, we could have an infrastructure that we want to leverage on the disease modeling community. So it's tied up into the infrastructure piece. The machine learning model, we've now done with Open Malaria. We can extend it further to other machine learning or AI models. And so the decision making is now looking at how can we leverage on the infrastructure, the machine learning, and the decision making to enable the researchers in the field to make optimal decisions in a timely fashion, and also in a way that it can be transferred across. And the resource governance, some of these decisions also need to be monetized, in the sense that who did what and what was done. So that is helpful in that aspect. So I'll drill down to the use case that we have. I showed this yesterday. I'll just skim through in the essence that the goal for this malaria scientist will have to alter the intervention in terms of, can I do what vaccines? Can I do insecticides treated bed nets? Can I do indoor spraying or changing L system? So these simulations is run over time. So based on what I've given, we built a system that the architecture is shown here, whereby we have the external engagement interface system where users come in and interact with the system. We have the message processor that really, if I'm going to run a simulation, what if someone else has run that simulation before? That message comes into a message processor, and the process engine is able now to look into that message and say, hey, Nelson, you don't have to run this simulation before. So-and-so has run this simulation before. Do you mind looking into their results so that it can help you advance? Or can that simulation build up on the knowledge from another simulation from the learning layer? So that, because this is a very high computing resource simulation, so it can take days. So you can imagine if all of us run it, and there could be different similarities, but if we can learn from each other, it can be quite useful. So that is why the process engine is there. We have the notification engine that notifies the user. We have the knowledge validator, whereby the experts coming in can validate given information and say this is valid. So the learning layer will build up on that expert's domain. Then we have the validation engine and, of course, the blockchain. And I'll just narrow down on the validation engine, since this is what extends the basic, the existing endorsement process in blockchain, and bring in the aspect of being able to make a decision based on the previous transactions. So the validation engine that we are looking, in our case, we have the distributed agents. And so the point is, can we recompute a state from a validated prior report? And also, if it's valid within a given threshold, then we endorse. If it's not within a given threshold, then we flag that as a probable, and in this case, probable back to be recomputed or to be validated by an external person, since it might be not within the suboptimal space. And so we can then validate and say that the validity of a given simulation over time is the validity of the average intermediate states. And this really is arguable in the sense that we need the initial point of saying an expert in a given domain will validate that. Then moving forward, we know that it's within a given aspect. And really looking into if you're going to do an intervention of vaccines, all of us will do an intervention of vaccines. And we have the model similar, demographic similar, entomology similar, a bit of variations here and there, but it should then not give you much difference further. And so that's what we have. And so looking at the implementation we have task clerk where users in the field upload the experiments, and then we have queues to manage those, and then we have the workers which are responsible now of simulating this, running these simulations. And so the message queues really help to bind the task clerk and the workers. And the task clerk is which receives requests from users. And then the data store is the one that once a worker has completed running an experiment, it's stored on the data store, and then the data store invokes the validation engine, which then helps to validate that simulation as being it's within a valid range or it's not within a valid range. So we're just adding a layer of a third high that can help us to, when you're running like 500 simulations, so you just need something that gives you that information. To sum it up, we've created what we have here really is just an interface for both to a malaria scientist and be able to give them a platform that leverages on the different aspects. And looking into the experiments, the visualization shows is like 144 workers running the open malaria model distributed across different clusters on IBM Cloud. And so each worker in this case performs a total of 8 open malaria simulations, generating a total of 1,152 results as a validation set. And so on average, based on the experts, they can say that it's on average, we can conclude that the results is valid. And with this initial data set, we then sought to experiment the platform that I gave out, that can we then say on this, can we identify which worker was not valid in the sense of the output. And so of these sources, we randomly did a subset of 10% of them as anomalous, and thus generate noisy rewards. So in that case, the experiment, a client then would go sample 500 policies and query the system for a corresponding reward. And then the system then employs a worker to evaluate the reward against those 500 policies corresponding to and the validation that should be done by the validation engine. So basically, you sample 500 policies, and then you need to get a reward of a given policy that you've selected. And so the validation engine then helps you to validate that output. And so in the experiment, for each of the experiments we did, we collected validation statistics and then deviation statistics. And the deviation statistics, we're just looking at the Euclidean distance between the current state X and the average state recomputed by the validation engine over time. So the higher the deviation, the less reliable the reported state, and then therein more likely of an erroneous report. And so with these distributions, then we sought out to detect any deviation from the data set that we had. Looking at the average validation set, using we see that the CDF, that is the cumulative distribution function of anomalous workers, is biased in comparison to that of honest workers. And in this case, it really indicates that anomalous sources income more invalidations than honest workers. Really, in this case, as expected, because the probability of invalidation in the presence of anomalous sources is higher. And we can also observe that the presence of anomalous sources affect the validation statistics of a honest worker. Because they might tend to undergo more invalidations than they would really otherwise. So it's just a way of running the validation statistics. And also we did the deviation statistic. In this case, it shows also the cumulative distribution function of average number of deviation per worker, depending on the worker being anomaly or honest. And really the plot then further suggests that the deviation statistic of, really the deviation statistics are clearly differentiable between the two groups. And so the CDF anomaly of the CDF of the anomaly worker, we can see the red curve rises slower. That is the anomalies of the anomalies incur far more deviations per source than honest worker. And so we then, now that we have the validation statistics and the deviation statistics, we then sought the Kolmogorov's-Smirnov test, which helps to check the distribution similarity between two types of anomalies. The not biased sources are greater than 0 and then unbiased. And so it was really able to validate this in the sense that the deviation and the validation profiles are really different, and that was really helpful moving forward. Then we moved forward and also did the problem of other than the problem of anomaly detection, as clustering into two clusters. So where we have the KNN classifier to determine honest and anomalous workers. In this case, the validation deviation profile as a feature representation, and in particular, we use the total variational distance between this probability distribution as a notion of distance in the KNN classifier. The plot then further suggests that when we have performance of unbiased, that's when C is equals to 0. And then we have the varying degrees of bias when C is greater than 0. So when we can see that when C is equals to 0, the anomalous sources behave like unbiased noisy compute nodes, and so there's ADA to detect in that case as indicated by its misdetection and the false alarm probabilities. We also have when C is equals to 2, the false alarm probability worsens with the minimal to no improvement in misdetection probability. C is equals to 5 is like kind of a sweet spot where we observe that the anomaly detection gets significantly easier as the bias becomes more recognizable through the invalidation profile. And of course, as you increment the C, the anomaly sources are so heavily biased, that's when C is equals to 10 and 15, that they end up creating far more frequent invalidations, which make the classifier honest sources anomalies. Thus, the false alarm probability increases. In addition to that, we also did detecting in terms of recomputation. So we look at the average number of computes per state, or approximate computes per simulation as a function of the validation tolerance in the x-axis. So for the varying sizes of endorsers set as hem. And so with the decreasing validation tolerance, we can observe that the computation overhead also increases sharply. So this is really due to the computational framework we used. Open malaria increases significance quite variance, so the collision probability is also lower, so therein increasing the chance of invalidation, which means if it's invalidated, it also have to be recomputed again because it doesn't go within a given threshold. And so in conclusion and possible future work, we've established, this is an extension of the work yesterday, so we've just established validating intermediate states, then performing distributed endorsement using reported previous states, and also the possible extension that we want to have into other epidemiological malaria or other epidemiological disease modeling frameworks. And also the interesting aspect also we want to look into is the learning layer bit of the framework, in the sense that can we have partially computed results so that I don't have to run an experiment from 0, but I can pick up from where someone else left that experiment and compute that. So that is all that we have. I'll take any questions.
All right, thank you, Nelson. So we do have time for a couple of questions now. Okay, I do have a question. So you mentioned about the anomalous worker in this context. Can you please explain why they want to, behave in a malicious fashion here? Like, I mean, first of all, why do they want? Because it's a permission setup, right? We're not talking about like a public setup with unknown identities. We know the people that are actively participating in the process. So can you please explain why?
Yeah, so that's a good point, in the sense that some of these experiments, like why would we want to identify malicious, and it's we know everyone. And the case here is really contributed by the fact that most of these projects that they're running, it's really highly funded by different governments and entities. So the decision to make to fund like spraying bed nets, it's like costing millions of dollars to run that experiment. So at the end of the day, when you're making that decision, you need to be sure that this is the optimal decision to be made because of quite a number of factors. And so it can be biased in the sense that as a disease malaria scientist, I can make a decision, but that money has gone that would have gone to help someone else. So it was just looking at can we be certain of us funding this simulation. And also, second point to that as well is because there are cases of reported health workers who just misuse and run different simulations just for their own, of course, vested interest. So it's majorly based on the region that you are in, the probability of situations that might occur in that case.
Okay, got it. Okay, great. Thanks, Nelson. Okay, let us thank the speaker once again. Okay, so we'll move on to the second technical talk of this session, which is going to be given by Dr. Anselm, and he's going to talk about a response to the United Nations CITES blockchain challenge, incremental and integrative PoA-based permit exchange. Anselm is a postdoctoral researcher in the Information Systems Engineering group at TU Berlin, and he received my PhD from TU Berlin in computer engineering. And his research interests include off-chaining techniques and the application and integration of blockchain technology into real-world applications and systems. Anselm, floor is yours.
Hello, everyone. Thank you for the introduction. And yeah, today I will present you our response to the United Nations CITES blockchain challenge. We worked on it TU Berlin together with Adesso Swiss. Unfortunately, I have to start with very, very depressing news. As you may heard, this month a study was presented that over 1 million species are threatened by extinction. There are different reasons for that. And one of the reasons is that such species are traded. For example, if you have a leather band for your watch or have a nice bag that is made of crocodile leather, this probably is from one of the endangered species. There is a convention on the trade, which is the CITES, the Convention on International Trade in Endangered Species of Wild Fauna and Flora. In some countries, like in Germany, where I'm from, it's better known under the term Washington Convention. And it's already in place since 1975, and it's covered by, or is engaged by 183 nations, and it covers over 5,000 animal species and over 30,000 plant species. But as you can imagine, the system is not perfect. That's why we had those depressing rules. As most of you won't know the system, I will give you a quick intro how it works. So that's CITES in a nutshell, how the whole process works. So let's assume you're an exporter and you want to export, for example, crocodile leather of a crocodile that's not from the wild, but you have grown. And if you want to export it, you cannot simply ship it to another country. You need an export permit, which is a piece of paper. And what happens is that CITES has local authorities in each country, so it's a very highly decentralized process. And if you want to export such a regulated species, what you first have to do is you have to go to your local CITES management authority and ask for this permit. If it's legal to export this specimen, you will get this permit, which is a literal piece of paper. I will show you in a minute. And this permit will accompany the good while it travels. And when you import your good, it will probably be checked at customs that it's legal to bring in the product into the country. And the importer will report the import to its local CITES authority. Both authorities manage their the imports and exports in their own database. So every country has its own database on what's imported and what's exported. And in the end of the year, their imports and exports are reported to the CITES Secretariat. They will make a listing and check if you have, or if a country has exceeded its quotas or not. So you probably can already imagine what the problem is about this whole process that is completely paper-based. As you can see, this is an example for such a permit, and this is an example I found on the internet that this exact permit was used in some fraud of exporting and trading a species that's not allowed to be traded. And there are different factors that is possible to do with such paper permits. You can forge them, you can falsify them. Sometimes you can use it multiple times. And of course, if you are exporting from a highly corrupt country, you can simply buy such a permit. The CITES obviously by themselves realized that this system is highly prone to corruption and everything. So what they did, they heard about blockchain technology, but on their own they don't have the expertise and everything to come up with the system. So what they did is they openly posted a blockchain challenge. This is quoted from the challenge, but it summarizes it very, very decently. So we saw this challenge and thought that this is a very, very good cause. So we looked a little bit deeper in it. And the first thing we did is to check, does it make sense to use blockchain in this application? So we looked a little bit closer to everything. And we found out that it fits for a blockchain scenario. Why does it fit? So first of all, CITES is very, very highly decentralized. You do not have a single authority who says this trading is allowed, this is not allowed. Every country does it on its own, and there's no one who can tell a country you are allowed or you are not allowed to create a permit. Maybe in the end of the year you will be punished for creating permits, but you cannot disallow a country to permit exports or things like that. Then obviously one of the biggest issue is trust. Trust is very, very limited. Maybe also between countries, you know, not all countries have very high standards. Some countries are highly corrupt. So maybe it's not good to trust some of the countries that are participating in the system. Another point is that transparency is maybe something that is highly desirable. As you can imagine, third parties might want to look into the trades and check if everything is right. So maybe that's something we also can do through blockchain technology. And lastly, the decision finding between the different countries is highly protracted. So what currently happens is that all the CITES members meet every 3 years and do decisions and discuss everything. So we thought with this checklist, okay, we can try to build a system that is much better. So we went back and looked a little bit to find out what the requirements are. And something that from our perspective stood out is this part, that the system should be based on the current paper-based business process. So what we try to do is to come up with a system that is as minimal disruptive as possible. And to do it very, very short, this is the architecture we came up with. As you can see, what we did is we replaced the individual databases that every country have through a blockchain, and we replaced the paper permit simply through a hash. So a paper permit is now represented, not the paper permit, but the permit to export a good is now represented through a permit that is held on the blockchain, which is identified through a hash. Now, instead of giving the exporter a paper permit, the management authority of the exporting country will give the exporter the hash, which could, for example, be represented in a QR code, like we did in our prototype. If you look into the paper, there is a link to a video where you can see how it works in reality. And now, instead of the piece of paper, the link to the permit on the blockchain will accompany the good through its traveling. Now, in addition to be able to check the permit, it is also possible for a third party. For example, here it's customs, but could also be a different non-governmental organization who can check if the permits are the way they are supposed to be. Furthermore, as you can see, now everything is collected in one blockchain, so not every country has to maintain its own database. So it's much easier to track everything. Maybe a little bit more details regarding our implementation. So we built our prototype on the Ethereum blockchain. We used the proof of authority. So we ran a private instance of the Ethereum blockchain. There were two main reasons to use Ethereum. First of all, when we started to implementing, we were not quite sure how the use case looks like, whether we want to do it in a public blockchain or private blockchain. So we went with Ethereum to have the opportunity to later on maybe migrate or start the whole process also on a public blockchain. And on the other hand, the proof of authority, as it is right now, somehow fits the CITES structure. So the idea, for example, could be that every country runs its own authority node in the network. Furthermore, for the prototype, we implemented two front ends to be able to show CITES or give CITES an idea what is possible, how the whole process, how it actually works in the real world looks like. So we built one prototype that one front-end prototype that is fully web-based, and we also built a front-end prototype that can be used on a mobile device that is on a native client. We also implemented this simple account management. As you can imagine, you have different accounts who are allowed to create permits, you have accounts who are allowed to process permits, so you somehow have to differentiate who is allowed to write and who is only allowed to read. Obviously, the core is that we have implemented the permit creation process, so everything that was done on paper before is now possible to do in a smart contract. So we changed as little as possible, so the permit in the smart contracts has exactly the same information as the paper permit has today. And lastly, we did two test deployments. We did one on our private infrastructure to see how it is to set up, how easy it is to set up. And we also tried a deployment on the Azure cloud, thinking that maybe some of the countries will not host their own infrastructure, but will use cloud infrastructure. We were invited by the United Nations Environmental Protection Environmental Program, which is CITES is part of, and we presented our prototype. This was in November, and back then, and still ongoing, we have some discussions with CITES with interesting outcomes. First of all, probably not surprising for most of you, the blockchain approach is superior to the paper-based approach. First of all, you cannot forge anymore any permits, so it's much safer, but also easier because those papers you saw, they are special kinds of paper, and it's lengthy to process because it takes some time to get it, because you have to get it physically to export. But there are also other benefits. For example, now a live tracking almost in real time would be possible. the process as it is right now, you only see at the end of the year how much trade was going on, from which country to which country was shipped what. With the blockchain system, you would be able to see it in real time, well, almost real time. We also find out that most challenges that arises with introducing such a system are not necessarily blockchain related. So there are many challenges to introduce. For example, one other benefit of the whole system was, to our surprise, that was simply not possible anymore to put in a species that does not exist by simply having a drop-down list in the front end. As it looks like today, it's already an issue that the paper permit is filled how it is supposed to be filled. And we also came to the conclusion that there will be probably not one single blockchain instance. This will hold all the permits. Probably there will be several, one grouped about trade region. So we will expect that, for example, Europe will have its own blockchain instance, that Southeast Asia will have its own, that Northern America will have its own, which on the other hand arises new challenges. We will have to look into the futures how to migrate permits from one blockchain instance to another blockchain instance. There are much more discussion outcomes. For example, we also found out that when transitioning such a process to a blockchain-based process, it's nice to know how the whole process works. I just showed you very briefly in the beginning how the process works. When you look even much deeper into it, we found out that the process is a little bit different all around the world, depending on the countries. In some countries, customs checks the permit. In some countries, there are other authorities who check it. In some countries, they will keep track of all the imports. In some countries, they check if the number's right that is on the permit. In some countries, they don't. So there are differences in all the countries, which makes it a little bit more challenging to transform the existing process to a blockchain-based process. Another thing we learned, we also heard in the keynote a little bit, that it's not so easy to introduce new technology into a logistics process. So paper-based there is still the golden standard, and it's hard to convince people to go with something else. So it has to have a really big benefit to convince people to use it. And lastly, the access management might be challenging also depending on the region. In some regions like Southeast Asia, they already have account management for trading companies in place. So there it would be easy to just give an interface to use the existing account management. In other regions, it doesn't simply exist, and we have to come up with a solution, for example, how to give customs access to the whole system, because it's already, customs has so many tasks and they will not bother with a completely new system. So our next step is even deeper integration of paper permits. I haven't showed you here because of lack of time how we integrated paper permits. If you're interested, we have described it in the paper. But we want to have an even deeper integration, for example, through fingerprinting existing permits to be able to link an actual piece of paper to the blockchain. We will probably focus on specific trade regions. Currently, we are looking into Europe and Southeast Asia. Why those regions? Well, Europe is special because you have one big trade region that consists of many countries, and so you may have different customs involved bringing goods into the same region where the goods can flow freely. And Southeast Asia is interesting because they are already they are already experimenting with blockchain technologies on their borders. For example, some countries have a single window of trade where not only products covered by CITES go through, but every good has to go through. And lastly, I already talked a little bit about it. We have to develop an access permission strategy, to allow who is able to write permits, who's able to process permits, and also come up with a strategy for a transporting company to look into whether the goods they are supposed to transport are legal to transport or not. So thank you for your attention. And of course, if you want to get in touch and help us to protect nature and go forward with this project, I would be very, very happy to talk to you.
Thanks, Sonsom. That is right on time. Do we have any questions from the audience?
Okay, thank you very much. So I have a question is, did you operate your system in the real society?
Say again?
I mean, did you run your system in the real environment? I mean, did any user use your system? And then I see that you use the Ethereum platform. Did you use the public or private? Because now I also research about Ethereum, but the private, but I don't know how, because in the Ethereum private blockchain, so all the users should be in the same network domain. It is a different network domain, so we cannot connect with each other. So in case you use a private Ethereum, so...
Okay, first question, no, the system is not live because it's very, very hard to implement. So just to give you an example, CITES tries to establish an electronic trade system between two countries. They are building it for 10 years now. So this is something that really takes a lot of time to implement and go live. And your other question, as it is right now, it uses a private setup for the Ethereum blockchain. So we have private nodes that are connected to each other. The idea later on is that, for example, every country has its own Ethereum node, and those nodes of, at most, the 183 countries are connected among each other. But like I said, this will probably not happen, and you will have cluster of different blockchain instances that we have to come up with a way to migrate permits between them.
Yes, so you use the private Ethereum, yes. So can you connect several users in different internet domain?
What do you mean?
For example, you use private, but for example, you have 3 nodes. And one node in your labs and another node maybe in your homes.
Yeah. You connect them. It's easy. It's over the internet. So.
Oh, really?
Yeah, it's no problem.
Okay, so I would like to.
So that's also what we actually did. So we ran it on Azure and we ran it in our lab, but they had public IP addresses, so it wouldn't have mattered whether they stood just beneath each other or on the other side of the world.
Okay. Yes, thank you very much.
Great. Any other question?
Yeah, thanks for the talk. It could be some nasty question, but if I assume that these rules about protecting those or endangered species will be reflected on the smart contract, and joining those protection program is coming into the smart contract and complying with the rules there, then do you also think about how to persuade or enforce joining into this smart contract program for the countries who are either unable to or not willing to comply with those kind of rules, because those countries might consider this as a infringement upon their sovereign right, or so, yeah.
So yes, actually we thought a lot about this issue. We came up with different strategies. We are not clear yet which is the best one. It's also something we have to discuss. So first of all, we tried to maintain the process as much as it is. So we also thought about tokenization. We thought about automatically enforcing those quotas. But it would be easy to do it through a smart contract when a country reaches its limit, just to disallow to create new permits. But we didn't implement it because of this, because today each country can do as ever it's like. Then there's another reason to permit countries. Potentially, it is easier to maintain this infrastructure because you could, for example, share an Ethereum node. You do not necessarily have to run your own Ethereum node, or it may be easier to just get a guy who runs the Ethereum node for you than getting a guy who runs a highly specialized software or people who have to process paper permits. And last but not least, which might be interesting for some countries, is that you can prove that you are obeying it. So obviously this will not be for the countries who do fraud, but once you have maybe a critical mass of countries that are doing it, you cannot deny it, because then implicitly you will acknowledge that you do something wrong. But this is a highly political and highly complicated process where we have to be very, very careful. It's not a technical challenge, basically, but a very, very social challenge.
Right, thanks, Anselm. So in the interest of time, I would like to thank Anselm and invite the next speaker. So our next speaker is gonna present his work, a blockchain-based scientific publishing platform, which will be presented by Thomas Bosek. Yeah, so while Thomas is setting it up, I'll introduce him. Thomas is a professor for distributed systems and ledgers at the HSR Hochschule for Technik, Rapperswil. He's a blockchain researcher and CTO of Accelera. And he is also involved in Modem.io AG, which is a blockchain startup that combines IoT sensor devices with blockchains. And prior to his involvement at Hochschule for Technik Rapperswil, he was the head of peer-to-peer and distributed systems at the communication systems group of the University of Zurich. Thomas, the floor is yours.
Good. Thanks for the introduction. There you are. And in this talk, I'm going to show you how we want to improve scientific publishing. There are a couple of problems in scientific publishing. One of the problems is that there is the lack of contribution. So, for example, as a reviewer, you're not being properly credited. For example, if you work as a TPC, you do reviews. Sometimes you get to be on the list as a TPC, which is nice, but basically you work for free. So this is one of the issues. The question is, where is the money? So who has the money? And in the publishing system, there we have the authors. They need to pay for their papers, so they need to pay the publishers. The publishers get the money. Also, if a researcher wants to access the papers, the universities typically, they need to also pay a fee or pay a subscription to those publishers. So for the publishers, it's actually a very good business case because they get all the money. It's not a good business case for the researcher and for the universities. So this is one of the issues. Another issue is that we have a low incentive to publish negative results, meaning if we figure out that a mechanism X is not working, this is not publishable. So if we figure out, hey, I tried this, it didn't work, probably you cannot publish it. So I haven't heard in this conference
talk that some mechanism didn't work, didn't achieve the results you were expecting. So this is a problem. The next problem related to that is that we have a reproducibility problem. There was a survey by Nature that stated that over 70% of the researchers were actually not able to reproduce experiments from other scientists. And what we want to do is we want to redesign the incentives in scientific publishing. So what we want to do is to incentivize proper contribution and also incentivize validation work. So that meaning that you do reproducibility studies, that you re-implement something that another researcher did, but also contradicting studies saying, okay, this didn't work, we tried, but we couldn't reproduce the results. So that's why we came up with the Eureka platform, and we have the following use case in mind. In this use case, we have the following stakeholders. We have the authors, we have the editors, and we have the reviewers. So first, the authors, they want to submit a manuscript. So down here, we have a convenience layer. This convenience layer is designed that it adds for a better user experience. We designed the system in that way that we actually can work without the convenience layer. It's just not convenient anymore. So it works without the server, but for convenience, we have it in there. So the author submits his manuscript. He enters his data. He can say if it's a resubmission or if it's a new submission, puts in the URL where this PDF can be found, and also the number of reviewers he wants to have, and some additional reviewers, non-editor approved reviewers that he can enter. So during the submission, there are some sanity checks, meaning that the system checks if the authors have enough tokens. The PDF has some references in there. Here we see, for example, this is my Eureka address, which is a base 58 of an Ethereum address. This you can put inside the paper, then it's then it works without the convenience layer. If you don't have that, you can always go and look for the authors in the convenience layer and figure out what the Eureka address of this author is. You can also add more references if you like, and then you submit the manuscript, meaning that you trigger a function on the smart contract. You need, of course, to pay also Eureka tokens, and then the process starts. We have here our convenience layer, listens for events. If such an event happened, if there was a submitted manuscript, the server will get notified and then sends an email to the editor. This could also go directly, but as I said, it's more convenient to send an email out to the editor. The editor gets this submission and does also sanity check, sees if it's a real paper or if it's some kind of an automated paper. Can also check here the addresses, if they make sense, if they are the addresses of these authors. Then he can select the reviewers and starts the review process. And this also will trigger, again, the smart contract. And then again, if this happens, the convenience layer here will notify, will figure out, hey, there was an event, I need to do something, and the Eureka server will send an email to the reviewers asking, hey, there's a review, you have been assigned, do you want to accept or not? The reviewers can then decide. If they decide to accept, they do the review, they read the paper and come up with a score. this score then is persisted on the blockchain itself, not the review itself, so not the comments you have for the paper, but only the final result. So if it's an accept or reject and what the score was, this is then stored in a smart contract. And if you have enough reviewers that accept the paper, then again the editor gets notified and he can then accept or reject, or if the smart contract is written in that way that it's automatically accepted, then the editor will be notified that this paper was accepted. As a result, this process is very transparent. It's stored in the blockchain, but only the metadata. So not the paper isn't stored in the blockchain, also not the detailed reviews, but just the result is stored on the blockchain. So how does the token flow look like? We propose the following fee distribution. This is just a proposal, can look completely different. So we have the tokens that the author pay, can be, let's say, $500 US. And here we have a distribution where we say, for example, that 10% goes to maintaining the Eureka platform, 40% of that will go to the reviewers that did the review, 10% goes for the handling editor, 20% for the referenced authors. So if you reference an author, if you reference 10 authors, then it will be split, this 20%, among these 10 authors. And what could also be done is, for example, that 20% will be locked up for a year, for 2 years, in case of somebody invalidates this work, figures out, hey, that's wrong what they figured out. And in that case, this 20% will then go to these researchers who did the invalidation work. So that means the author, when he submits a paper, gets accepted, he has a publicly time-stamped paper. He also has a public record that it was reviewed, that it was accepted. And if the author was a referenced author, here if you have references, then they will also get tokens. That means you will also earn some tokens if you're being referenced. So the more references you get, the more tokens you have. The reviewers, they also have a public record. So everything they do is recorded on the blockchain, and they have Eureka tokens as well. The editor has also Eureka tokens and also public record of what he did. So that means the Eureka token is more than just a token, it's also a public track record of what you did. We have implemented that system. We use in the front end React, MetaMask via Web3j. We use Ethereum, obviously we're using the testnet, and in the backend we have Node and Mongo DB as the database. I won't go too much into details because this was presented on Tuesday. We had a demo session. So if you want to see it again, please talk to me or talk to Andy, if I can see him. Over there, yeah. One of the design issues or design principles we followed is that we need to have a good user experience. And for that, for the token design, for example, we try to make it as easy as possible. So for the contract, we used ERC 677, which means that you can call contracts and pay tokens from that contracts in one transaction. And we used ERC 865, which means that you can pay your gas with tokens. This is quite important because if you use tokens, if you want to transfer tokens, if you want to interact with the blockchain, you always need ethers as well, you need gas. With that, you can offer a service that you only need tokens and you don't need gas in order to issue transactions. So we have two kinds of contracts. We have the token contract with ERC 677 and ERC 865. From these contracts, we can call them the journal contracts or the platform contracts, and interact via those two contracts with the system. So the question is now, why do we need a blockchain for that? It could actually be done with the technology that we have without a blockchain. There are, however, a couple of issues. For example, these tokens that go to the reference reviewers, those are microtransactions, and micropayments in our banking system. It's feasible to a certain degree. You could do it, for example, if you have a small amount, you can accumulate the account until you reach a certain limit. For example, Swiss 50 US dollars, and once you reach that limit, you can pay this 50 US dollars to the authors. That would be feasible. Banking transactions can also be expensive. They can be slow. They can be expensive. If you want, for example, send money to Africa or India, it's not that easy. It might also be a bit more expensive than if it's within Europe, for example. Here the solution is to increase this threshold. That could be a solution. And also, if you are in the banking system, you have this IBAN number. If you change your bank, this IBAN changes. That means you need to keep these numbers in sync, the authors with the IBAN, and if it changes, then you need to make sure that you also have the right IBAN number for the author, because what can happen then if you send money, the money bounces back, and then you don't know where to send the money to. Or you can simply use a blockchain. That's what we did. We used Ethereum, and we solved all these problems here. And another question is, why did we need our own token? Why can't we just use a native asset, for example, Ethers? Technically, it would be the same, so we don't need a token. However, for marketing reasons, it's much easier. For example, if you want to give away gift cards with some Eureka tokens, it's much easier than to give out these Eureka tokens, because you can basically create them out of thin air. And if you have Ethers, you would need to pay Ethers, and this would be much more expensive. That's it from my side. Do you have any questions?
Thank you, Thomas. You actually finished 5 minutes in advance. Okay, great. Do you have any questions? Oh, we have a question there. Yeah. Maybe, yeah.
Yeah.
What?
So I was wondering, would it work with double-blind review process?
It doesn't work with double blind.
Okay.
We want to make it as transparent as possible. We tried to design a system which is double blind, but then we figured out, okay, this gets too complicated. And then we went to the direction into full transparency.
Okay, and one more. So who chooses the reviewers? Or anyone can just review?
No, so the reviewer is chosen by the editor, but you can also suggest, as an author, some other reviewers that the editor might accept or not.
Okay. And one last question. Do you think that putting money into the whole system would create, some like people now are crazy about being referenced or being reviewers because there is actual money involved? Wouldn't it kind of spoil the whole system where it's more a service than... It's more a philosophical question.
We don't know. We think we can improve it. That's our belief, but if this will work or not, we only can try and then see if it works or not.
Okay, thank you.
Okay, we have a question there.
Hello.
There.
Actually, my question is quite aligned with the one that he proposed. Actually, how do you ensure that all the process is fair and users cannot collude? So, for example, I mean, I can create one reviewer profile. I can have another author profile. how can I ensure that I cannot ending up reviewing my own paper or colleagues of mine pushing all the system? I mean, there is some anonymization, mixing. How can you ensure this?
The same way as we do it now. So it's not fully automated. I mean, the editor still has a list of reviewers. Those reviewers, if you're in a community, you know probably most of these reviewers. So there's also kind of this trust, and this you cannot fully automate. If you have a fully automated system, then you can create multiple identities, and then you can start to try to cheat the system. So here we still rely on trust. That means it's not fully automated. So there's still human interaction, which is important here.
So you try to mimic the real world, some more or less. Okay, it's fair. I understand it. Okay, so in this case, how you ensure that everyone is who he claims to be? I mean, yeah, the editors have his own, in the real world their own reviewers, blah blah blah. How do you conduct this? I mean, in a journal nowadays, you can misbehave, behave, but everything is later reflected in your profile. I mean, the people will know it. How you can ensure that these fake profiles are not really appearing in the blockchain?
I mean, preventing it, it's kind of difficult, but it's good if you can detect that it's a fake profile. I mean, I can create 10 profiles, nobody can prevent that. But the idea is that through transparency you figure out, okay, this is actually, he did some real work, and for the other fake profiles that you should somehow notice that they're fake. So that's the key. But preventing it, it's probably not possible.
So you think it's better, not a proactive, but better analyzing the behavior of the system through some kind of heuristics to detect the misbehavior or the...
And through human interaction. So the editor, for example, for this conference, if you look at the TPC, they know each other, they know, okay, they do good work, and so it's fully automation is not possible. There needs to be human interaction, and with this human interaction, you can also somehow fight these fake profiles.
Okay, thank you, thank you.
Yeah, I think your system is fantastic from both sides as an editor and as a reviewer myself. I've been not paid for, but one interesting impact on your system is if we are not into a more commercialized publishing, and your system is pushing that further into commercialization of publishing, is that prestige of publishing from an academia viewpoint is now out of the window?
It is somehow, yeah. I mean, it is a commercial business. If you look at the publishers, they make good money, they make lots of money. And as a scientist, you do this for the fame, you do the reviews basically for free. And changing this, I think there could be a benefit in the system. I mean, I don't know how it will turn out. We just try and see what happens. Yeah. Okay.
Okay, we
Yes.
have time for one question.
Hi. So, may I ask you how you deal with the minor and major revisions? Because papers are usually not accepted in the original form, and do require some resolution through the blockchain, or no? Because with your incentivization scheme, the reviewers may recommend to cite their works in order to increase their profit. It's the natural incentives.
Yeah.
So
could happen in the system that we have today as well. But here you have a monetary incentive. Probably here it's a bit higher, this incentive. I don't know. I don't think so, but we'll figure this out. And yes, there is a resubmission process. So here in the very first step, you actually say if it is a resubmission or not. Because if it is a resubmission, you can reference your old paper, then you can also see the highlights, see the differences, and also this could have an influence on how much tokens you need to pay. For example, if it's a resubmission, you can say instead of the full fee, you pay then some, I don't know, 1/3 or half of it. So you can actually say that it's already been submitted and this is a new submission. So we have this in place.
Okay, so you can even exclude the reviewer's citations or references from rewarding.
You can then have the reviewer says, please add me as a reviewer, then you can do a resubmit and then the reviewer is in, yes.
Okay, thank you.
You could do.
All right, great. So let us thank the speaker once again. If you have more questions, Thomas will be around to answer, I guess. Okay, so that brings us to the end of the fifth technical session. So I'll hand it over to the chair.